All right, so in this video, we are going to look at the focus directrix definition of the conics. Oh, we already know the focus directrix definition of the parabola. That is when the distance from a point on the parabola is the distance from the directrix is equal to the distance from the focus. But believe it or not, the ellipse and the hyperbola both also have a focus directrix definition, which introduces the concept of eccentricity, which we usually denote with the letter E. You will learn in this video that ellipse has an eccentricity less than 1. The parabola has an eccentricity equal to 1, and the hyperbola has eccentricity greater than 1. You might already be thinking, hey, what is eccentricity? Oh, the parabola is equal to 1, so you might be able to conjecture what the eccentricity is, but we are going to get into the definition in the next page and then look at the ellipse, parabola, and hyperbola individually. This will be a pretty quick video, so let's go ahead and get started. All right, so the eccentricity definition, given a line, which we're going to call the directrix, and a point, which we're going to call the focus, and a locus of points, right? These points make up the conic section. All right, those are our givens. The eccentricity is the ratio of the distance from the conic to the focus to the distance from the conic to the directrix. Let me write that out. The ratio of the distance from the conic section to the focus to the distance from the conic to the directrix. Let me go ahead and draw a picture and make this make a little bit more sense. All right, so let's draw this picture. I'm going to give myself a directrix. Mine happens to be a vertical directrix, but it could go in any which direction. I'm going to give myself a focus, so directrix, focus, all right? And then the conic section, all right, whatever it may be, all right, ellipse, circle, parabola, hyperbola, like this could be a parabola. You could see how it might go on, but it might eventually curl back around. It might be an ellipse, or it might have that sharper feel and end up being a hyperbola. So this conic section here, what I am interested in is the distance from the focus to the conic section, which I'm going to call D1, and the distance the conic is, perpendicular distance the conic is from the directrix. All right, I'm going to call this D2. And the eccentricity, therefore, is this ratio, D1 to D2. Here with my picture, D1 looks a little bit smaller than D2, so this eccentricity is going to be a number smaller than 1. But that number could be anything. It could be larger than 1, it could be smaller than 1, it could be equal to 1. I'll leave that for you to ponder for a second. But here is what our eccentricity is. It's this ratio of the focus distance and the directrix distance to the conic. All right, I've just made a pretty powerful claim. I've claimed that this is going to create a conic. This is in agreement with the definitions of the conics that we already have. This can kind of clearly be related to the parabola, right? If I take this definition, if D1 and D2 are equal, if the eccentricity is 1, then we are the definition of a parabola that we've already looked at, right? The distances are equal, regardless of the point that you pick on the parabola. But I've also claimed that this is in agreement with the ellipse and the hyperbola formulas. So let's go ahead and justify that. Let's give ourselves a directrix. let's give ourselves a focus. And I'm actually going to say that this focus is going to be at the origin. All right, this is going to be our focus. It's at the origin. And this directrix here, I'm going to put it at x equals negative k. So some arbitrary value to the left of the origin. So here is some arbitrary conic section. All right, let me go ahead and make it a little bit more symmetric. All right, this might be a little bit of an ellipse. It might find its way back around. You can kind of imagine that this might be an ellipse, but it might also be a parabola, and it might be a hyperbola. We don't really know. We need to know these distances. And so let's pick an arbitrary point on the conic section, x comma y, and we want to compare the distances, d1, which is this distance, with this distance right here, a little bit off, sorry, d2. All right, so what is d1? Well, that's just a distance formula question. What's the distance from 0, 0 to x comma y? That's going to be the square root of x minus 0, x squared, plus y minus 0, or y squared. What is d2? D2 is a little bit more tricky. It's less straightforward, but we can take advantage of the fact that we have a formula for the directrix. Right? The distance from the focus to the directrix is k. Okay, the distance from the origin to this line is k. The focus has been centered at the origin. All right, and then, but we want this green distance, d2, so we need this distance right here. Well, what's that distance? Well, that distance is just x, right? Because this is y. That's what the definition of this coordinate is. It's horizontal movement and it's vertical movement. So this distance d2 ends up being k plus x. All right, so the question that stands now is the equation E, which is a constant, d1, the square root of x squared plus y squared, over k plus x, is this in agreement with the conic section formulas that we already have? All right, is this a conic? All right, well, let's just do some algebra and see if it works. So we have E is equal to the square root of x squared plus y squared over, I believe it was k plus x. Let me just double check. Yeah, k plus x, cool. I'm going to multiply both sides by k plus x. We got E times k plus x. And then I have x squared plus y squared. All right, very often when we're looking at a formula and we want to understand it a little bit more, we got to get rid of those square roots. So let's square both sides. We're going to get E squared times k plus x quantity squared, and that's going to be equal to x squared plus y squared. Cool. I'm going to go ahead and expand the left-hand side. So we're going to get E squared times k squared plus 2kx plus x squared. And then I'm going to take this to the next page. But I'm going to I'm going to distribute this e squared and move everything to the other hand side, the right-hand side, and we are going to kind of interpret this thing. So we're going to get an x squared. Oh, we have a y squared here. We're going to have x squared plus y squared minus e squared k squared minus 2e squared kx minus e squared x squared. Cool. All right, let's do a little bit more. Let's combine those x squared terms. So I'm going to factor out an x squared of all the x squared terms. That's right here and right here. So I'm going to get, 1 minus e squared. And then I'm going to look at my y squared terms, just y squared. And then I have a minus e squared k squared, and I have a minus 2e squared kx. All right, so I have an x squared term and a y squared term. That's the key, x squared and y squared. This is consistent with the equations that we had prior. All right, if you give me a value E and a value K, all right, if you give me a location of a directrix in relation to the focus at 0, 0, and then you give me a ratio E, we will have a quadratic in X and Y, and then you can do what we've done in the past, complete the square, and you will get one of the conic sections in their graphable form. All right, which one do you get though? All right, if you have E is less than 1, what happens? Well, if E is less than 1, you're going to get 1 minus E squared. A number less than 1 squared is a number less than 1. 1 minus E squared, this number right here will be positive, and Y squared is positive. So you're going to have a X squared and a Y squared. You're going to complete the square. You're going to get an ellipse. If E is less than 1, you're going to get an ellipse. You're going to have a positive coefficient in front of X squared. If E is equal to 1, the X squared term is going to go away. 1 minus 1 squared, that's 0. You're just going to have a Y squared term and then a linear X squared term. This is a parabola. And then last, if E is greater than 1, the X squared is going to become negative, and you're going to get a hyperbola. You're going to have a positive Y squared and a negative X squared. You're going to have a hyperbola with a vertical transverse axis. Real quick, some pictures. If I have E is greater than 1, I'm going to have a directrix. I'm going to have a focus. But E being greater than 1 tells me that the distance from the focus to the conic, the distance is going to be larger than the distance from the conic to the directrix. So this would be a viable point right here. This distance right here is larger than this distance, and for all those points, you're going to get a hyperbola here. All right. What we already knew, the parabola. I have a directrix here. I have a focus right here. This is a viable point here, but then also like about right there, this distance right here, and this distance right here, those are equal. So this is going to be that perfect parabolic behavior. All right. So we have over here. Let me go ahead and write this actually. Hyperbola. We have a parabola, and then lastly, if I have this directrix and I have a focus, and the distance is closer to the focus than it is to the directrix, if this distance is larger than this distance, what I'm going to get is I'm going to get an ellipse. Let me do my best job at drawing an ellipse. And believe it or not, the ellipse and also the hyperbola are going to have 2 foci and 2 directrix. Directrices, I don't know. I don't know the plural of directrix. Throw that in the comment section. Don't forget to like and subscribe. All right, so there you have it. We have a hyperbola, parabola, and ellipse. And I'm forgetting to write things all over the place. This is when E is equal to 1. The ratio is the same. And this is when E is less than 1. The ratio of the distance from the focus is smaller than the distance to the directrix. Right? So we have the hyperbola, the parabola, and the ellipse based on this new definition, eccentricity. All right, so we have those old definitions. The constant difference is always the same, or the difference is constant. The distance, well, our old parabola definition was this. And then the ellipse, the old one was the any point on the ellipse, the sum of the distances from foci is constant. Now we have this eccentricity definition. So we have new definitions for each of these conics. So the last thing I'm going to do in this video, just a quick example. Find the equation of the conic with eccentricity 3. So you already know what the conic is based on this 3. Go ahead and answer that in your head. And focus at 0, 0, directrix at y equals 2. So we have all the information that we need to determine this conic. All right, so let's quickly just sketch a quick picture of this thing. So we have a horizontal directrix this time at y equals 2. We have the focus, so this is the directrix, We have the focus at 0, 0. And we have eccentricity 3. So the distance from the focus is going to be 3 times as far as the distance from the conic to the directrix. So this distance right here is d1, d2. The distance d1 is 3 times the distance that it is d2. So there you go. There's your conic. D1, what's that? 0 to the point. Let's go ahead and call this point arbitrarily, x comma y. This distance, d1, is x squared plus y squared. This is the distance from xy to 0, 0. And this distance right here, well, this distance right here is given to us as 2. So this distance right here, it's 2 minus whatever this distance is, which is this distance, which is y. So we have 2 minus y. 2 minus y. All right, I didn't quite get back to white, but I will continue. So let's square both sides. We're going to get x squared plus y squared is equal to 9 times 4 minus, what is that going to be? 2 times y, so 4y, and then plus y squared. And then this equation, I'm going to take it to the next page. We got x squared, we got y squared. We got 9 times 4, 36, minus 9 times 4, 36y, and then plus 9y squared. And then moving everything to the left-hand side, we're going to get x squared. We are going to get a negative 8y squared. We are going to get plus 36y minus 36 is equal to 0. And this conic, let's go ahead and put it in its standard form. So let's complete the square. We got x squared. X squared is already complete. Let's move the 36 to the right-hand side. I actually don't know why I moved it to the left-hand side in the first place. Or whatever. All right, let's factor out that negative 8. It's already screaming hyperbola, by the way. We have this minus y squared. If I factor out an 8, going to get a negative. That's negative, right? Yep, negative 4.5y. And then let's go ahead and complete the square. So we're going to get x squared minus 8. Y, so what do we need to add? Y squared, what do we need to add? Probably should have written this in fraction form in the first place. We got 9 halves, so plus this number divided by 2 squared, so 9 fourths. It's going to be 81 sixteenths. So we're adding 81 sixteenths times negative 8 to the other side. So minus 8 times 81 sixteenths. And that leaves us with minus 9 fourths squared. Oh, so the square was actually never necessary. My bad. And that's equal to, ends up being negative 9 halves. Not a problem. Let's go ahead and finish this. Let's divide both sides by negative 9 halves. And we get negative x squared divided by 9 halves. We're going to have a 1 over here. And then over here, we're going to have negative 8 divided by negative 9 halves, which ends up being, it's positive 16/9, so we're dividing by it. So we're going to get a y minus 9 fourths squared divided by 9 sixteenths. We're multiplying by 69, so we're dividing by 9 sixteenths. All right, there's our a squared value. There's our b squared value. There's our center. And there's our hyperbola formula. All right, so eccentricity being 3 led to a hyperbola as expected. And here is that exact hyperbola formula given the ratio as well as the equation of the directrix and the focus being at 0, 0. You could do this for any focus and directrix combination. Yeah, there you have it. I'm going to stop there. I just wanted to introduce the idea of eccentricity and how it relates to the ellipse, the parabola, and the hyperbola. Every conic has an eccentricity, and this is like a new definition of the conic. there you have it. I'm going to stop there. Have a great day.